Welcome back. We now start a new module where we deal with multiple variables, with multivariate analysis. And before we get into specific clustering techniques, we'll consider dimension reduction methods. And specifically, there will be 3 lectures devoted to dimension reduction methods. The first one is a quick review of some important notions, specifically the notion of the cursive dimensionality, and then a review of some matrix algebra notions, which you may be familiar with, and then you can just skip it. And then the other 2 lectures, which are the main fare for this module, is one devoted to principal component analysis, and the other one devoted to multi-dimensional scaling, or distance preserving methods, as they're called. So this brief review will just go over the notion of cursive dimensionality first. And what is the cursive dimensionality? It's a major problem when dealing with multivariate analysis. And this is not always recognized because we tend to work in 2 or even in 3 dimensions, where we can clearly see the data points. But imagine working with 100 variables and a couple million observations. Then this is not the same situation anymore. And Bellman introduced this concept, and in a nutshell what it means is that techniques that work fine in low dimensions break down, either completely break down in high dimensions, or become so complex in high dimensions that they are impractical. So for example, if the complexity increases exponentially with the number of variables, then we're very quickly out of luck in terms of computing something in a reasonable time. You can think of this as if you have to forecast the weather for tomorrow and it takes 2 days to run your model, then it's no use. So it's the same kind of concept, that some things that work really well in low dimensions fail to work in higher dimensions. So to make this concrete, consider the example of searching for the maximum of a function by brute force, basically by taking a bunch of evaluation points and then finding the one with the highest value and then possibly repeating that on a subsequent interval. Different search methods, like bisection search, are based on this approach, a shortcut to this approach, actually. So what it boils down to is that if you have, say, 10 equally spaced evaluation points in one dimension, then if you have k dimensions, you would need 10 to the power k evaluation points. For example, if you had 10 variables, 10 dimensions in your multivariate attribute space, then you would need 10 billion points to evaluate that. So clearly this becomes infeasible very quickly. And to visualize this, to illustrate this, here is the one-dimensional problem. So we have a function between 0 and 10. We try to find the maximum of the function. What we do is we have 10 equally spaced points, and we find the value, and we find the one with the highest value. Very simple. Now let's extend this principle to 2 dimensions. And here we are. 1 dimension, 2nd dimension. Again, 10 equally spaced points in each dimension. But now we already have 100 points. In 3 dimensions, we have 1,000 points. And so it goes on. So very quickly, this becomes impractical in high dimensions. There are a couple of other examples that I found in this very useful book by Hastie, Tibshirani, and Friedman. And think about this a second. If you want to be able to search a certain fraction of a unit volume, a unit line, and if the points are randomly, uniformly spaced through there, how far do you have to go to search a given fraction of the total data volume? So in a line, it's linear. So if you want to find 50% of the data volume, you have to go half the distance. If you wanted to find 20% of the data volume, you go 20% of the distance. But very quickly, this deteriorates. So let's take 10% of the data volume. Linear is 10. 2 dimensions, we're here. We have to search about 30% of the square. 3 dimensions, we're very close to half of the volume of the unit cube. So in this little example here, to find 10% of the data points, we would have to search half this box. And it gets even worse. In 10 dimensions, we would have to search 80% of the data, 10-dimensional data hyperspace. So this is an example of something that seems very reasonable, just direct search in low dimensions, but very quickly becomes impractical in high dimensions. Another example, and one that we run into quite often, is KNearest Neighbors. And for example, in 1 dimension, the distance required to find the nearest neighbor is fairly small. To go from 1 to 2 dimensions, we have to search in a circle, and now we see already the distance is twice as large. And it gets even worse as we get in higher dimensions, which relates to this other concept, which is the empty space problem. And essentially what it means is that in high dimensions, the attribute space, so the counterpart of a data cube in 3 dimensions, is you have 10 dimensions, it's a 10-dimensional hyperspace. Essentially, it's mostly empty. And the data points are very far from each other. There's large distances between the data points, and they're also distributed in very weird ways. In this book by Lee and Verleisen that is referred to in the workbook, in the lab notes, there's some descriptions of really weird spiky things and situations where all the points are at the edge of the hyperspace, things that we don't see in 1 and 2 dimensions, but that become increasingly common in very high dimensions. Another aspect related to this has to do again with our nearest neighbors, in that nearest neighbors in high dimensional spaces are not necessarily nearest neighbors in low dimensional spaces. And this will impact us when we try to reduce the dimensionality of the problem, which is what dimension reduction is about, by, in a sense, projecting the higher dimensional space to the low dimensional space. To make this concrete, you may recall from the intro spatial data science course that we looked at points in the 3D data cube, and even though they looked very close from a given perspective, say a projection in a particular 2-dimensional space, they were not close at all in true 3-dimensional space. Hence the need to rotate and do all these kinds of manipulations. So the empty space problem, to illustrate this very simply, here we have some randomly uniform generated data points in 1 dimension, and we do this 3 times. So these points are relatively close together, but then if you consider them in the 3-dimensional data cube, you have all this empty space in between. And so that is an illustration of what we call the empty space problem. So in a nutshell, what this means is that working in multivariate high dimensions is a different ballgame from working in 2 or 3 dimensions. And we don't always realize that because we use these kinds of examples in 2 or 3 dimensions to make things concrete. In 10, 20-dimensional space, you cannot really imagine it anymore, at least most people can't. And so then things get very complicated in terms of representation and so on. So what do we do about this? The strategies that we'll discuss in the following 2 lectures are all about reducing the dimension of the attribute space, of the variable space. So we have, let's say, 10 variables, which is a 10-dimensional variable space. We want to reduce that to a small number of variables, say maybe 2 or 3, that approximate the information content from the 10 variables as closely as possible. And one example of this, and a very common example, is principal components analysis. Principal components are essentially replacements of the original variables. They are functions of the original variables. In fact, they're a weighted average of the original variables, but they capture a large part, in fact, the largest possible part of the variance embedded in the original variables. And the information that is in the covariance matrix among, say, the 10 variables is approximated as closely as possible by reducing these 10 variables to a handful of principal components that have as close to the information content of the original variables as possible. And of course, the advantage of these principal components is, first of all, instead of working in 10-dimensional attribute space, we work in two or three-dimensional attribute space, which is a lot easier, and we can visualize it. Another advantage is that there may be a lot of collinearity, multi-collinearity among the 10 variables, whereas by construction, as we'll see in the next lecture, the principal components are uncorrelated. Then that is one set of methods, and then this other set of methods we call distance-preserving methods, and because they're basically a way to think about distance in attribute space. So if you just keep it simple and think of a 3D data cube, you can compute the distance between the points in a 3D data cube. Now, the purpose of distance-preserving methods is to reduce the dimensionality of the problem by representing these points in a lower dimensional attribute space. Technically, this is called embedding the points in a lower dimensional space. So instead of being, say, in 10 dimensions, we show them in 2 dimensions. And in order to do that, the way we do that is we try to mimic the relative positions in 10 dimensions. In other words, the distances between the observations in 10 dimensions as closely as possible in the lower dimensions. So we try to preserve the relative positioning from the high dimension in a lower dimension. Of course, this is not going to be ideal, but that is the objective of distance-preserving methods. And we will consider 2 in particular: classic multidimensional scaling and a method called TSNE, which comes out of machine learning, which stands for stochastic neighbor embedding. Then another method is projection pursuit, which we won't cover in this course because there's only so much we can talk about. So before we get into this, I wanted to just have a very quick refresher of some basic matrix algebra notions. I'm assuming most of you are familiar with this, so you can readily skip this, but sometimes it's useful to put things refreshed so we're all on the same page. So a matrix is basically a box, a table with numbers organized by rows and columns. And a particular form of a matrix is a vector, which just has either a column or a row. And what we're particularly will be focusing on is the product of a matrix with a vector. And you may recall from your matrix algebra that you get this product by multiplying the first element in the first row with the first element in the vector plus the second element in the first row with the second element in the vector, and so on. So a matrix vector product is written as A for this 2 by 2 matrix and V for this 2 by 1 matrix, row number first, column number second. And one thing you have to respect in matrix multiplication is that the inner dimensions have to match. So if we have 2 by 2 for this one, we need 2 by 1 for the second one. And the end result is a combination of the outside dimensions. So 2 by 2 times 2 by 1 yields 2 by 1. And what is actually going on under the hood in matrix multiplication is two operations. One is rescaling, the other one is rotation. So let's look at this in some more detail. Here we have a vector. It is represented as a line, usually with a little arrow point, and it is in 2 dimensions. So this vector has value 1 for the x dimension, value 2 for the y dimension. So this is a visual representation of the vector. What happens when we multiply this vector by a scalar? We just move it out along the same direction. So multiplication by a scalar is just rescaling, changing the length of the vector. Multiplication of a vector, pre-multiplication of a vector by a matrix involves 2 operations. First of all, rotation, and then rescaling. So if we work out this product of our matrix A times the vector V, we see the matching elements being multiplied and added, we end up with the 0.75. So we have a rotation downward and an extension, a rescaling. So why do I give this example? Because I want to get to a concept that unfortunately tends to confuse a lot of people, and that's the concept of eigenvalues and eigenvectors. And these are things that exist for square matrices, any matrix that has the same number of rows as the number of columns. And eigenvalues and eigenvalues are a pair. For every eigenvalue, there's an eigenvector, and vice versa. And the eigenvectors are scaled such that their sum of squares equal 1. That's just basically to be able to solve the problem. And what is the problem? The problem is to find a vector and an associated scalar value so that when we pre-multiply the vector with this matrix A, we simply have a rescaling. So in other words, if we do this operation with this particular vector, rather than rotating and extending, we only have extension of the original vector V. So this is a tricky problem. What is the solution? How do we find this particular lambda and the particular V? And actually, there is not a simple solution. There's many algorithms to find this numerically. But the essence of the concept of an eigenvalue and an eigenvector is to find a specific vector that, when pre-multiplied by this matrix, does not rotate and only rescales, and rescales by exactly the magnitude lambda in this symbol. So formally, this is expressed as such, that the matrix times the vector equals the eigenvalue times the vector. And just to illustrate this, so there's, as I mentioned, there's specialized algorithms to find these eigenvectors and eigenvalues, and I've computed them here for our example. These are the 2 eigenvectors, and these are the matching eigenvalues. So if we multiply our matrix A, the same matrix, 1, 3, 3, 2, times this eigenvector, so here's the first element, here's the second element, we get this result, 2.9 and 3.5 essentially. Now, if we multiply the vector, the same eigenvector, this one here, by its associated eigenvalue, we get the exact same result. In other words, A times V equals lambda times V. That is essentially what eigenvalues and eigenvectors do. Now, why are these so important? Because they allow us to decompose an actual square matrix into elements that are easily manipulated, and that's why we do this. And this is called the spectral decomposition. Later on, we'll see spectral clustering. Well, spectral clustering is directly related to spectral decomposition, to eigenvalues and eigenvectors. Okay, let's see what this involves. So we have our fundamental expression, we have our square matrix, our eigenvector, our eigenvalue, and the eigenvector. So if we do this for every eigenvalue, each square matrix has as many eigenvalues as its dimension. So the 2 by 2 matrix, we have 2 eigenvalues with 2 associated eigenvectors. So if we write them all together, so we write this expression for the first eigenvector, then for the second eigenvector, we can write it concisely as this. And A is our original matrix. V is also a matrix now of the same dimensions as A, where each column is the eigenvector. So each column is one of these V's that multiplies to lambda V, and the lambda we stick in the diagonal of this matrix G. So matrix G is also of the same dimensions, in our case 2 by 2. So we have the original matrix A, we have an equal dimension matrix V, which consists of the eigenvectors as the columns. Then we have the eigenvectors as the columns here, and a diagonal matrix with the eigenvalues on the diagonal. And now we can play some matrix algebra magic. We post-multiply each part by V prime. V prime is the transpose of V, basically with the rows and columns switched around. And as I mentioned, these eigenvectors are specific. They are orthogonal to each other, which means that if you multiply one eigenvector with itself, the result is 1. If you multiply an eigenvector with another eigenvector, the result is 0. In other words, the product of V times V prime is an identity matrix, so the result is just the matrix A. So on the left-hand side, we have the original matrix A that we started with. On the right-hand side, we post-multiply with V prime, so we get this expression. Now this expression consists of the eigenvectors, the eigenvalues, and the eigenvectors again, but flipped around. So with just the eigenvectors and the eigenvalues, we can represent our original square matrix. Now, why would we want to do this? For example, this gives us a way to get a square root of a matrix. How would you compute the square root of a matrix? It's not obvious. It's not the square root of each element. It is, in fact, V times the square root of G times V prime. Same, what is the power of a matrix? Well, the power of a matrix can be represented as V, G to the power, and V prime. So this device, I call it a device because it's something that we use over and over, is called the spectral decomposition of a square matrix. Now, there is one square matrix that we're particularly interested in, and that is the covariance matrix. The covariance matrix is X prime X. And we can take this covariance matrix, which is always square, even though we have n observations and say p variables, this X prime X matrix is P times P. And we can write this using the spectral decomposition as the product of a matrix with the eigenvectors, a diagonal matrix with the eigenvalues, and the eigenvectors transposed. So this would be the spectral decomposition of the covariance matrix, which we'll encounter in many places in what follows. And then there's another very important decomposition, which is called the singular value decomposition. And I'll spare you the technical details, but in essence, it's another way to represent a matrix, but now not a square matrix, any kind of matrix, as a product of some useful matrices that have particular properties. And the singular value decomposition of a general matrix with n rows and p columns is the product of 3 matrices. And 2 of these we recognize, well, one of them we recognize. The matrix V is the same dimension as the number of columns, the matrix D is also square with the same dimension as the number of columns, and the matrix U is of the same dimension as the original data set, the original n times p matrix X. What's special is that both U and V are orthogonal. In other words, if you multiply their rows by each other, the same row, the result is 1. Different rows, the result is 0. And V is also orthogonal with the same result. D is a diagonal matrix. So we decompose the matrix into 3 particular matrices. I won't dwell on the technical details of what these mean and what they represent, but they are in essence a series of rescalings and rotations. And in the lab notes, I have a little animation that illustrates this. So the operation that is involved when you multiply a vector by this matrix can be decomposed in particular actions associated with each of these matrices: rescalings, reprojections, and re-rotations. So U is n by p, D is diagonal p by p, V is square p by p. Okay. Now, how does this help us? So notice how the singular value decomposition is applied to the original data set, not to a square matrix. But we will be dealing with this square matrix. That's our covariance matrix again. So how do we get something that's useful from this? Well, remember, our decomposition of X is U d V prime. Then the transpose of X is V d U prime, right? So X prime X can be represented by this product of 6 matrices. Only we know, we just posited this, that U is orthogonal. So the product of U prime with U is 1, is an identity matrix. D is diagonal, so the product of 2 diagonal matrices is a new diagonal matrix with the squares of the elements on the diagonal. So now we have something that looks very familiar. This looks exactly like the spectral decomposition that we had for X prime X. And in fact, it is the spectral decomposition of X prime X with V as a p by p matrix of eigenvectors and D square as a p by p matrix of eigenvalues. So D square are the eigenvalues. So this is an alternative way of getting the spectral decomposition of X prime X. And there's some numerical reasons to prefer the singular value decomposition to the original spectral decomposition, which is based on the eigenvalues. So for the original spectral decomposition, we need to compute the eigenvalues and the eigenvectors, which has some numerical issues. If we do a singular value decomposition of X, this gets us U, D, and V. We actually don't need U. We just need D square, actually, and V. So we can construct the eigenvalues and eigenvectors by not focusing on the square matrix itself, but by focusing on the original data matrix X. And this has several numerical advantages that I won't dwell on, but is just what I wanted to do here is just present a couple of concepts that will pop up over and over again in what follows, and it's just good to have a sense of which is which. And cursive dimensionality will mess things up over and over again. This little bit of matrix algebra pertains primarily to eigenvalues and eigenvectors, which are very useful in characterizing particularly square matrices through the spectral decomposition and its counterpart, the singular value decomposition. So next we'll delve into distance we delve into principal components first. See you then. Bye.